Hello and welcome to this video on stoichiometry. Stoichiometry is one of the awkward words used in chemistry that comes from Greek roots. The words roughly translate as element measure, with stoichon being element and metron means to measure. In chemistry, it is a shorthand summary of how calculations are done. That might sound strange to you if you only think of these equations as something like 1 plus 1 equals 2 or 2 times 2 equals 4. The problem with chemistry is that the reagents you begin with are not the products you finish with, and in some cases the numbers can change drastically. This makes a chemical equation more like algebra than it does anything else. In other words, stoichiometry has more similarity with x plus y equals z than it does 1 plus 1 equals 2. To get a viable equation in chemistry, you need to balance the equation. This means knowing how many moles or units of a reagent are needed to make the right number of products. This has been previously touched on in a video called Predicting Ethanol Yield from Sugar, where this exact approach was used. In that instance, each glucose molecule produces not one molecule as a product, but 4. This does not mean you need to put 4 glucose molecules in, just 1. Knowing this, you can then say that for every 1 mole or unit of glucose, you will get 2 of ethanol and 2 of CO2. This is an important thing to know. As mentioned earlier, it is why stoichiometry is more like algebra than anything else. On average, you will know what the reagents you put into an equation are and what the products should be. Now you have to balance the equation. This is a step that involves checking that everything adds up. Specifically, is there the right number of each element on both sides of the equation? An obvious problem is when a previously non-existent element shows up on one side of the equation but not the other. This compares the reagents and the product's final state. This also lets you count how many moles of reagents and products you have, which provides some idea of the yield percentage. To get the moles, you must take the weight of your reagents and divide by its molecular weight. Let's say you have water and carbon dioxide. Water weighs the same as 2 hydrogens and an oxygen, which is 1 plus 1 plus 16, or 18 grams per mole. Carbon dioxide is 16 plus 12 plus 12, or 40 grams per mole. Let's use water as an example of both this weight process and balancing the equation. To make water from pure elements, you would need the following equation: 2 moles of dihydrogen and 1 of dioxide. This produces 2 water molecules. This simple equation shows how chemical equations are like algebra, as each molecule is prefaced by how many units it has, and the number after each symbol is how many of the element are in each unit. If you were to only use a dihydrogen and a dioxide molecule, you would wind up with 1 free oxygen at the end. This fundamentally prevents the reaction from occurring in that manner, and you need to add another dihydrogen to it to get a balanced equation. This creates your ratios, which are important. If your ratios are the same, then everything is good. If not, you need to change the ratios, which is where chemistry crosses over into algebra. Think of the preface number for your moles of whatever compound, chemical, or elements as being like algebra's x equation. How many x's do you need to get y? Now, this is where things get interesting. Chemical equations. These can be facilitated by heat, a reaction gradient, or any other energy differential. Think of the Maillard reaction and how it works within a specific temperature range, where anything above this and the reaction does not occur, and anything below this and the reaction occurs at an incredibly slow rate. A common example of these reactions is magnesium and hydrochloric acid that produce hydrogen gas. An important note to make here is that of limiting reagents in any equation. The conversion of hydrochloric acid into hydrogen gas is dependent on how much magnesium is present. Too little and the hydrochloric acid won't all be used up, and so there is a reduced yield of hydrogen gas. Too much, the magnesium will be left over. The process works by having the chlorine bind with the magnesium, freeing up the hydrogen as an ion. You can see that in this equation. Stoichiometry is important for understanding and predicting reactions. It also ensures that you are using the right amount of all the reagents, which are like ingredients in a recipe. It will also tell you how effective you have been in your experiment. Has your reaction produced more or less than you expected? And is the amount of the product produced economical or viable in an industrial setting if you are not getting an adequate yield? Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions below.